are sailors and adventurers.
We're going beyond anywhere we ever went for Apollo.
Splashdown. Orion, back on Earth.
And there's a lot more coming.
Our destiny is always to go and see what's further and what's next.
There actually metal is being bent, shaped, formed to build the things that we're going to use.
We are going. This is reality.
NASA is at a historic inflection point, poised to begin the most significant series of science and human exploration missions in over a generation.
Astronauts will live and work in deep space, and will develop the science and technology to send the first humans to Mars.
I'm really looking forward to all the science we will conduct on the moon, the samples we'll bring back, the knowledge we'll gain from understanding the lunar environment better than we ever have before.
The more nations and companies at the moon, the more we learn, increasing our capabilities while strengthening things right here on Earth.
We are going to the moon to learn how to live on other planets for the benefit of all. Let's go.
So let's begin with the Artemis mission statement. That was Bill Nelson, the NASA administrator, giving you a call to the mission for Artemis, that this is humanity's return to the moon. And I'll read it as it's stated in the NASA Artemis plan. With Artemis missions, NASA will land the first woman and the first person of color on the moon, using innovative technologies to explore more of the lunar surface than ever before. We will collaborate with commercial and international partners and establish the first long-term presence on the moon. Then, we will use what we learn on and around the moon to take the next giant leap, sending the first astronauts to Mars. And with that, we get the idea and the framework for the Artemis missions that the goal isn't the moon. The goal is to go to Mars. And that's what we have in the forefront of our minds as NASA engineers and contractors, that this is our stepping stone to get us to Mars. So, to kind of frame, why do we want to go back to the moon? We've already been there. And one of the major reasons behind this has to do with the scale and distance of these missions. And so the question I ask is, well, how far away is the moon? Well, the moon is over 300,000 kilometers away. And so let's think about Mars then, that it doesn't seem that far away every day as we talk about it and we send rovers there, these unmanned missions, but it's significantly farther. We're talking about millions, tens to hundreds of millions of kilometers. And a typical metric that NASA engineers like to think about it whenever they think about Moon versus Mars missions is 2,000 times longer missions. And that's something to be reckoned with here. And I really like Wolfram Alpha and NASA's graphic here to get the scale for these distances that we're talking about. And you could line up the diameters of each of the planets all back to back between Earth and the Moon. Well, now let's multiply that 500 times and we get the kind of scale of what the distance between Earth and Mars. And remember, that's just the closest that they could be. That's during conjunction. And conjunction only happens about every 2 years, and that's something significant, that we have challenges that we have to face to be able to get to Mars. As you can see, at its farthest, it could be 400 million kilometers away, or even more, depending on the particular time in the orbit. Our travel distance is going to be farther than that because we're having to catch these planets and satellites like the moon while they're orbiting the sun, and we're also orbiting the sun. So it's not as if we can just draw a straight line between them and complete these missions. So thinking about Artemis, and going to Mars eventually, one of the things we really want to focus on in Artemis is learning how to do long-term space habitation and to kind of appreciate just how far we have to go and how difficult the problem is. Let's look at the minimum practical mission duration to go to the moon. And we're talking about 12 days. That's a day or two to travel to the moon, to do separation, rendezvous with a lander, go down to the surface for 7 to 8 hours, and then come up and travel back in a few days. And it has some practical considerations that if there's a problem and you're a few days away from Earth, you can abort your mission and go back. You're in this geocentric kind of coordinate frame that everything is centered around the Earth in this mission, so going back to the Earth is possible. But let's talk about the minimum practical Mars mission duration. We're looking at a minimum and best case scenario of 2 years, and these aren't my numbers. These are actually kind of hard to come across. You won't see them published in many articles because trying to figure out how long a mission could take constantly changes, and you'll see that later through the presentation that plans change and things happen, and we're constantly evolving at NASA to figure out how long a mission really can take. And so these are from a podcast I highly recommend. It's by NASA Johnson Space Center. It's Houston, We Have a Podcast. And this is the first episode of the Mission to Mars series. And they gave a good estimate of 2 years if you're lining up to conjunction. And that's substantially longer. You have the consideration that if something goes wrong, getting back to Earth in most cases is not going to be an option. And so how far are we right now in the consideration? How far can we go? Well, the longest human mission in space was 473 continuous days. So not too terribly much longer than a year. And so now we're going to have to do 2 years of sustainment and all the logistics that come with that. This is a substantial challenge, and NASA needs to do Artemis to lay all the groundwork, framework, and test to be able to support human life on a deep space mission to Mars. So I've talked about bio and life support systems, but I want to be very clear, I'm not an expert in those areas. I am an RF design engineer at a defense company called Coherent Technical Services Incorporated, CTSI. And my background is that I got my master's in electrical engineering, specifically RF integrated circuit design from Rice University in 2022. And I got my bachelor's in electrical engineering from LeTourneau University in 2021. Some of my past work is I am a former comm systems engineer for Jacobs as a contractor to NASA Johnson Space Center. Some of my interests, some of the background for me is I really like working on satellites. I've got the privilege to work on 2 CubeSats. I do a lot of work with software-defined radios, microwave devices, and RF integrated circuit design. And right now, my focus is on research on non-cooperative Starlink navigation, OneWeb navigation, and vehicle-to-vehicle networks. So if you hear a lot about radios in this presentation, it's because I love radios and devices like that. So bear with me, it comes up, and I love it. So the things that I did at NASA is I performed spectral management. So that's deciding where satellites can operate inside a spectrum, analyzing different satellites and spacecraft to ensure compliance with the FCC and NASA guidelines. And this is where we make sure that spacecrafts don't interfere with each other in critical operations, and that's very important for manned missions. There's a lot of work and time and expertise that's put into the management of all of these thousands of spacecraft out in orbit. I also did some preliminary radio designs for Gateway and did quite a bit of technical analysis and reviews for different parts of the Artemis mission and a lot of CubeSats. There are many out there, and there's quite a few things orbiting our Earth. I worked in Building 44 on NASA's Johnson Space Center campus. You can see it here. It was built in the second phase, and that's going to put it like mid-1960s. And so you've got a test lab here that's part of it that's really cool, that you've got an S-band antenna and several UHF antennas, and then two KA band antennas and their radomes. And what this was a state-of-the-art emulation lab for the shuttle. So this is where all the communication ideas and concepts were tested in reality, and this is still where we do quite a bit of the testing of the communications theory and putting it into practice and certifying it and testing it. So there's some really cool stuff that goes on in my department. I was part of the Avionics Systems Division's Wireless Communication and Systems branch. And that's a mouthful. And finally, you can see a picture of me in the cockpit of the shuttle mock-up for electronics testing. So this is where, in the shuttle era, they would, all the astronauts would run through real live tests of running the shuttle mission that they're about to go on. So that was a kind of a one-of-kind of experience that I just really love to be able to get to go and do that. So, continuing on, let's talk about each of Artemis's core mission elements. And there are quite a few here, and I'm going to try to go through, give a little piece of each of them, and keep the presentation rolling. So, the first piece is your transportation. How do you get to orbit? And that's the Space Launch System. The whole idea here is the spacecraft that you see here with the orange, burnt orange core stage and its boosters. This whole spacecraft is about the size of the Saturn V rockets back in the 60s and 70s. That the idea is we have larger spacecrafts now, like Orion, and Halo, that's going to be put into orbit. So we've got to increase our payload mass and volume capabilities to be able to support these Artemis and later Mars missions. Going on with this idea, you have the Orion crew vehicle, which is the astronauts' vehicle to actually travel into deep space. And this actually wasn't originally part of Artemis. This was a concept and device from, vehicle from the Constellation program, and I'll talk a little bit more about that later. But it's quite a bit larger and far more capable than the Apollo spacecraft. And you can see some great advancements like crew quarters, ability to easily sleep in the spacecraft, major upgrades in having independent guidance, navigation, and control. And that's a really big deal to take a lot of the load off of astronauts, especially as you're going into deep space. Then we talk about some of my favorite parts. And of course, it's antennas and radios. So you have the exploration ground systems. some major upgrades and maintenance had to be done to the launch pad 39B at Cape Canaveral, Florida. You have the mobile launcher and landing pads, a vehicle assembly building. They all have to be ready to be used on a regular basis again after quite a bit of downtime from the shuttle program. The Deep Space Network. This is one of my favorite topics to talk about and work with. And what it is it's 3 ground stations that help us communicate with anything in our solar system at all times. So you can see an object in our solar system at all times. However, this is not like your Wi-Fi network. You're not going to get gigabit speeds here. We're talking about around 10 to 100 megabits per second. And you're not talking about a lot of ground stations either. You're talking about antennas at Goldstone, Canberra, and Madrid. So this was a major upgrade to be able to get these kind of throughputs and support these very long distant, very high data intensive missions. The next piece of Artemis is that NASA's not doing Artemis alone. It is tightly integrated with commercial partners, and part of that is taking payloads to the lunar surface. And so you're going to see a lot more experiments and devices going to the moon. And with that, a piece of exploration is the Viper rover. And that is out of my expertise to really explain what the Viper rover does and what it's about. But excuse me. Some of the cool things are that the communication system was under a lot of test in the building that I was in, and I'm kind of glad I wasn't a part of it. It's a very hard challenge to work with rovers sometimes, but I learned a lot from the folks that were working on it in my building, and I have great respect for the work that they're doing. On Gateway, we're talking about more things that I really love to study and love to work on. Is the Gateway space station, which would be the first lunar orbiting space station. We have the first piece of it, the power and propulsion element. This is going to have your initial communications. It's going to have your propulsion, things like your thrusters, which are some really cool technology that's been developed for this, and it's a really high intensity, fast paced development that's going on to make better and better deep space propulsion ability. And so this is some state of the art equipment that's going to power up the space station. Then we have the main piece that I'll talk about, which is the Habitation and Logistics Outpost. That's HALO is its acronym, and that is the main quarters and living space, an area for the astronauts. It's the center of the space station. And so I'll talk a lot about this coming up in the presentation. The Deep Space Logistics Module, this is going to be helping with cargo and resupply, trash disposal, add some extra volume to the space station, and it will help make the space station sustainable throughout its lifetime. Then we have the Extravehicular Activity System, or EVA, and this required a totally new spacesuit, and you can look this up. I was there at Johnson Space Center whenever they revealed the new spacesuits, and they are this brilliant orange and black as they brought them out, but Don't fear, they're actually going to be white. They will be reflective and protect the astronauts from the intense heat radiation from the sun. So calm down on that just a little bit. It's mostly for the show and the pictures and wallpapers. But it's a serious upgrade to the EVA system from the Apollo era. That the backpacks weighed somewhere over 60 pounds on all the life support equipment, and they were massive, taking up all of this space, very bulky, hard to move in. The new EVA suits shrink that backpack size down quite a bit and really give a lot more mobility to the astronauts. So the next piece of this is the human landing system, and I'll talk about it a little bit later. This is just an artist concept from the very early days of Artemis planning, which it's evolved quite a bit, and I'll talk more about that. But this is how your astronauts are going to get from Gateway or from Orion down to the lunar surface, and it's got a lot of upgrades, again, especially in guidance, navigation, and control from the days of mostly hand-flown spacecraft with computer-aided navigation back in Apollo. The next is the Lunar Terrain Vehicle, LTV, but I more affectionately think of it as the Moon Buggy. So it's got some upgrades going as well, that being able to carry power to other devices, go a good bit faster. So that's going to be really cool to see that. Then something I really wish I'd gotten to work on at NASA is Lunar Ground Station. So imagine taking that deep space network and plopping a smaller version of it on the moon. That is epic to me, and the thought of creating that kind of a network to again further push our communications footprint out towards deep space and further into our solar system. That's going to be really, really cool, and it's going to be necessary to help support this next piece, which is LunaNet, which you can think of as like similar to Wi-Fi or cellular on the moon. And why the heck would you even need that? Well, we're planning to put quite a few devices on the moon, and tens to hundreds of experiments all at once, and sensors, and they need to move data. So part of that whole ground station and network and LunaNet is having satellites alongside Gateway to relay very high-speed data back to Earth. And so this is really cool, and it will support a lot of the science missions. So keep your eye on this, and I definitely will. And I loved getting to watch one of the LunaNet tests as they were trying to figure out how they were going to do this at Johnson Space Center. And I really wish I got to be a part of that. Finally, we have some. If you go to the it's the Space Center Houston, the public tourist trap right next to Johnson Space Center, you'll see the Habitable Mobility Platform, which is this large mobile laboratory that is going to be put on the moon and help do missions farther away from base. And speaking of base, the Foundation Surface Habitat is going to be the home base for astronauts on the surface of the moon. So this is where we begin to test those ideas of how do we keep humans alive in deep space on a different chunk of rock. So there's a lot that goes into that. With the same idea, remember the goal is to go to Mars. So we've got to have power. And so there's a couple of different ideas that will be tested from nuclear power. This particular one that's shown is a foil tube that you can easily transport in the logistics module or one of the government contractors bringing cargo and payload to the lunar surface. It can easily be transported and then unfold to give a large solar flux area availability. And then finally, the Lunar Surface Innovation Initiative is being able to learn how to live on a planet that has very few natural resources. And that whole idea is in situ resource utilization. And this is where you get to really cool research of how do you do things with what you have available. And one of my very close friends, Justin Sharp, was an intern at NASA while I was working there. Did some really cool stuff with, of all things, laundry. And you might laugh at that a little bit, but laundry is actually a very difficult thing to do well in space. You have a very finite amount of water that you can generate and recycle, and you're in a spacecraft. You're having, you have to maintain your guidance, navigation, and control, so you can't stick a washing machine up there. So there's a lot that goes into that, and how do you use what you have to live and sustain yourself? And there's more crazier ideas like blood in the water and things. So, there's some crazy stuff. Not all of it is completely sane. So take some time and look it up. It's really interesting stuff. And with that, I want to begin talking about each of the missions. So we'll start with Artemis 1 that was launched last year. And it was a successful mission. It was a total duration of 25 days, 10 hours. And this starts with launch in Cape Canaveral, Florida, and jettison of the core stage and rocket boosters. And then one loop, one loop around the Earth. And we have to be able to get up to speed. And then here at 7, we jettison out some of the CubeSat missions into trans-lunar injection orbit. And you have Orion separating from its propulsion stage, which is the ICPS, the Internal Cryogenic Propulsion Stage. And it is disposed by going around the moon and shot out into space, into very deep space, where it has a very, very low probability of having a significant collision with an important object. And so then the Orion capsule moves through trans-lunar injection and then enters into a distant retrograde orbit. So this is a type of orbit that allows you to very closely approach the surface of the moon and then use all of that stored up energy from approaching the moon to then slingshot yourself very far away, but then still slingshot yourself back around towards Earth. So this was a highly successful mission. It was launched on the 16th of November 2022, and you can see it launching from Cape Canaveral, Florida, with a really iconic picture right there. And my whole time at NASA, there was constantly videos playing of the Orion back on Earth splashdown, and it's just really iconic. It was a great motivator for everyone at NASA to keep doing what we're doing and making the great progress. And so, did we just send a flying rock around the moon? Well, because there are no people on it. Well, no, so we actually ended up sending Captain Moonikin's Campos, which is our mannequin that's retrofitted with quite a few different sensors and fluid flow measurements, lots of biomechanics and kinematic equipment to try to figure out how humans be affected in the launch of such a massive vehicle and traveling around the moon. And then you can also see the other passenger here, Snoopy, one of my favorite characters. We had pictures of Snoopy up all over NASA. I just love it. And he wasn't there just for a free ride. He was actually the zero gravity indicator. So he let the live stream monitors know when the astronauts would feel apparent gravity. So whenever you're actually going to feel a force rather than the apparent weightlessness in deep space. Another really cool science mission that happened on the Artemis 1 mission is this Callisto tech demo, where they put an Alexa into the spacecraft and kind of tested the back and forth interaction with high throughput video and audio through the Deep Space Network and relay satellites. And so I hate smart devices, but this was a really, really cool science mission. And I and I am glad to report it was successful. So the next stage that we're looking at for 2024 is Artemis 2, and this will be the first crewed mission to the moon since Apollo. And you can see that we have our crew that was announced recently. We have Reed Wiseman as the commander, Victor Glover as the pilot, Christina Cook as a mission specialist, and Jeremy Hansen as a mission specialist. If you're not familiar with NASA astronaut teams, that you're going to have a commander and a pilot that are primarily focused on operations, and you'll have mission specialists that are either engineers or scientists that are focused on doing these science missions and pushing knowledge forward through whatever the team is going to be doing. And they're all contributing to science, but these are kind of their focuses for these missions. And so now I want to kind of show an animation and talk through the trajectory for Artemis 2. And I've got to pull up my cheat sheet here because it's been about 6 months since I've been daily working with Artemis 2 trajectories. And it was a huge part of my work there at NASA to be looking at these as I'm analyzing different spacecraft that we're launching. So we start with a launch in Cape Canaveral, Florida, and we're going to jettison the rocket boosters, and we'll have MECO, which is main engine cutoff, and we'll have Orion and its propulsion stage do a perigee raise maneuver, which perigee is the closest approach to a body you're orbiting. And so you're going to then raise that by doing a complete revolution around the Earth. And at that point, it will do an apogee raise. So apogee is the farthest distance from your orbiting body. It will raise that to be able to exit Earth's orbit, and we'll do a proximity operations demonstration where the astronauts will actually separate the Orion spacecraft from its propulsion stage and then put it back together. And those are things that are best done with humans aboard. It really showcases the capabilities and flight readiness of the Orion spacecraft. So then we'll enter translunar injection, to where we'll cross over to the moon and go around it in that left to right fashion from the relative coordinate frame of the Earth. So this is where you get that Artemis arc. And then we'll return back to the Earth along a sort of symmetrical path. And then we will do our re-entry burn and deploy our heat shields to land in the Pacific just off the coast of California. Well, that was a mouthful. So, the next stage. And so this is where I want to mention that this is the plan as of January of this year. And NASA has to change plans quite a bit. I know that this changed several times while I was there for my 6 months there. And it probably is going to continue to change until everything in mission planning is finalized. And in 2 weeks, the science seminar will have a flight director from Mission Control at Johnson Space Center here at LeTourneau. So he'll be a great person to talk to about planning, plan again, and yet plan again. So let's talk about what NASA has in mind. And it's unclear for Artemis 3 whether if we'll have a crewed lunar landing, or if that will be pushed into Artemis 4. So keep your eyes out. I'm going to present it as it is given here, that they're planning on having it crewed in 2025. So in a similar fashion to Artemis 2, you have a launch from Cape Canaveral at probably a lower inclination here, and you'll have separation and enter into translunar injection. And whenever you arrive at the moon, we'll then have an outbound powered flyby that will put us into a near near, near rectilinear halo orbit. And that, I'll talk more about why that's important, but this is kind of testing the ability to maintain the orbit and to then get you really close to the surface to, at number 9, do lunar landing and put humans on the moon, and then still have Orion following this orbit while this is all going on. And then we'll have a typical return back to Earth and land off the coast of Baja California. So, Artemis 4. This is public information. It was posted by a NASA colleague online, so it's been released, but it's not final by any means. This is still heavily under work for Artemis 4. And so the general idea here is getting Gateway into orbit and have crew on Gateway. So this is not necessarily, may not be when Gateway arrives at the moon. That might arrive in a separate unmanned mission, but I'll present it as it's given, that we launch from Cape Canaveral with Orion attached to Halo. IHAB. Sorry, we have IHAB on here. It depends. Actually depends. It could be IHAB, PPE, Halo. I think it's presented as IHAB on here. So IHAB launching. And so we send IHAB out into the near Halo rectilinear orbit, have rendezvous with Gateway that's already here, and to then attach the IHAB onto the Gateway space station, and then do a lunar landing with a crew on the moon, go back up to Gateway, and then return back to Earth, landing in a little bit farther out, most likely in the Pacific Ocean. So let's talk about one of my favorite aspects of Artemis, and that is the Gateway Lunar Space Station, which will be the first lunar space station. And this is really awesome. This is a very accurate public rendering of Gateway, and look at all the antennas. It's wonderful. I really like this. And just like the International Space Station, it's a highly collaborative international project between NASA, the Canadian Space Agency, European Space Agency, and Japanese Space Agency. So there's a lot of folks working on this. And NASA likes to think of it as a foundation in deep space, that it's an assembly of elements that will orbit the lunar surface and give capabilities to global human space exploration. And it's going to really be the catalyst for sustained deep space investigations and giving us access to the lunar surface and eventually aiding in missions to Mars. And you can see here Orion docking with the Gateway airlock. So really cool. Refueling. Sorry, that's the refueling module, actually. So let's take a little bit bigger picture look at this. Again, that Artemis isn't just about going to the moon. It's the focus of these missions, but the ultimate goal is to go to Mars. So we start with Artemis 1, having the first human-rated spacecraft to go to the moon in this century. And that's almost a little over 30 years, I believe. And then Artemis 2 is getting humans into orbit around the moon. And then we have Gateway going up around the moon and getting established. And Artemis 3 through 5 is getting humans out into deep space and doing the initial tests, getting humans down to the surface. So the beginning of the lunar surface experiments are going to be a lot of these unmanned missions like Viper that will begin to explore and ready the surface for humans. Looking a little bit further into here is continuing to expand Gateway and build on its capabilities, and to eventually have a permanent surface habitation and power generation, rovers and things like that on the surface. And this is all because Gateway is going to give us that outpost in the great beyond of deep space. So this is current as of October of last year, and so a lot of these names and companies will change, and most of that is proprietary on who's currently there. It's kind of like a game of who's on first, and I'm on second. So we look at some of the pieces that we have. That power and propulsion element that's going to give us the maneuverability and generation of power for the whole spacecraft. We have Halo, which is the center that you think of kind of where the astronauts are primarily going to be most of the time. You have the refueler that will come and go to help provide the propulsion ability for the space station. And then you'll have your logistics module, which at the time was going to be the Dragon XL from SpaceX. We'll see what happens with that. You have the airlock, which will allow different spacecrafts to dock and undock. And part of that, you have a separate airlock as part of the International Habitation module that will come with Orion. And then you have the human landing system that I'll talk about a little bit later, but this is the general reference diagram. That's what will take us to and from the surface of the moon. And you'll have most likely SpaceX doing the heavy hauling to get a lot of these modules to Gateway, including the initial, but we'll see how it goes. It's a constantly dynamic and changing space. And finally, one of the coolest systems here is the Gateway External Robotics System, or Canadarm3. So the International Space Station has these robotic arms built by the Canadian Space Agency. You had Canadarm1 and 2 on two different sides of the ISS, and then this will be the third one. And so we're going to talk a little bit about that as I show you kind of the build-up. So you have the co-manifested payload, PPE, and Halo arriving together unmanned. Then Orion and IHAB joining them, and Orion will depart and go on back to Earth with the crew. Then the logistics module will deliver the Canadian External Robotic Arm. So this is a really cool part that it can actually move across the space station. It can be used to help deploy different antennas and pieces and components. So we have the human landing system come in and join on one of the airlocks here on the Halo module. Then Orion will return with the refueling module and some more telecommunications equipment. So we have our human lander go ahead and leave, and it will come back from the surface of the moon, and our crew will go back home. And so we'll have our first moon landing with the human landing system at that point. And this is the plan so far. We'll see what happens. So we have the human landing system undock, and with that we'll have the logistic module also leave. And so these are freeing up airlocks to bring in new logistic modules and changing the orientation to support different mission goals as we go on. So we rotate it around a little bit. We'll have Orion deliver another airlock module that will allow for different entrances into IHAB, and we'll have another lunar surface mission, and we'll have our astronauts going back home. And you kind of see the pattern that yearly basis kind of missions of going to the lunar surface. And so we clear out an airlock here for another shift of supplies. We jettison off the logistics module. And we bring a new logistics module on a different port. And we bring back the HLS. So, we're looking, this is probably in the late 2020s here, very late or early 2030s. And so we have another lunar surface mission. And all the while, you have lots and lots of uncrewed missions going directly to the lunar surface as well. And so our crew goes back home again. We do another return and switch, getting more logistic modules. And so that's the plan so far. We'll see what happens, and a lot of this is still being planned as we go. So let's get an idea for the size. That the ISS it can be thought of like a 6-bedroom house, this massive human-made structure. And Gateway would be thought of like a 1-bedroom condo. It's significantly smaller, but very adequate for the missions going to deep space. The module I'll focus on is the one that I got to work on briefly as far as preliminary designs, dealing with the high-rate lunar communication system. And this is really cool getting to see this in Building 9 in Johnson Space Center. This is the engineering mock-up, and it's to help get a sense of real space and practical design aspects that are hard to assess just in drawings and CAD. And so you can see the high-rate Ka band antenna models up here, and it's just really cool to get to see that begin to be built and all of the progress made here. So I promised a little tidbit on the near rectilinear halo orbit. It's a buzzword around NASA that science folks love to talk about it. But as far as the purpose for me and the work that I do, is that the primary advantage it's going to give for communications is being able to access a view of Earth at all times. And that's critical for things like LunaNet and the Deep Space Network access, because we're sending humans, not just rovers, to the moon, and we're not simply visiting for a very short time, like in Apollo. So it's important to be able to see the Earth. And the human lander systems, here are two concepts, two different bids that are currently in development. You have the SpaceX Starship lunar lander and the Blue Origin Blue Moon lunar lander. And we'll see which ones end up getting used. This is all still being built and decided, so very capable designs from both, and I'm really going to be watching to see which one comes to life. The sheer size of the SpaceX one is massive. Look at the flag. It's quite remarkable. So because LeTourneau University is a Christian university, I want to take the time, because I have the privilege to talk about what God does through all of this. And the lesson that I've learned is that God changes our plans. So my plan for my career was to intern for Lockheed, go design antennas and radios for planes, graduate with my bachelor's from LeTourneau, go work with Lockheed and Raytheon in electronic warfare, build epic electronic weapons and defenses, and then work while I'm getting my master's. And I was like, that's a great plan. Well, NASA had a great plan as well. Back in 2004, the Bush administration initiated Constellation. They began to design Ares 1 to carry the Orion spacecraft to the ISS, Ares 5 to carry Orion and Altair lunar lander to the moon, and they plan to be back at the moon in 2019. Well, God had a different plan for both me and NASA. So in my life, God's plan for my career was instead to intern for CTSI and do some RF and position navigation and timing research. Eventually graduating from LeTourneau with my EE and half of my master's degree already completed. And then taking more turns in unexpectedness, going to Rice to get my master's, and in the process getting married to the love of my life, my beautiful wife. And And then finishing my master's is, by surprise, working at NASA. I couldn't have guessed ever working for NASA, and it really became a surprise that the opportunity was open and to get to go and do this kind of work. And then God wasn't finished changing my plans and my vision for life. I got the opportunity to return to Longview and to research the bleeding edge of navigation technology and actually build really cool satellite technology. Well, let's look at how God changed the plans that NASA had. So in 2010, the Obama administration canceled Constellation. It was far behind budget. There was no realistic pathway back to the moon through that program's catalyst. And so it had to be dropped. And in 2017, the Trump administration established Artemis, and a realistic plan to the moon was created. And we're seeing real progress here. That we're seeing that Artemis 1 was launched in 2022. But God isn't done changing things and really starting to challenge NASA to look at what its commercial partners can do, that SpaceX will be replacing the SLS. And so we look into the future and we pray and hope to have Artemis 2 in 2024, to have humans orbit the Earth, and praying that we have humans on the moon in 2025. So once again, I would like to thank you for taking the time to explore the Artemis missions with me, giving me your attention. It's been a pleasure and an honor to get to present at LeTourneau University Science Seminar. And it has been an honor to be a part of what God's doing at NASA.